Hello, welcome to note set number 13. In this set of notes we will continue our discussion of Fourier series, and in particular we'll get into all the details of Fourier series. And I should point out that here I'm stating explicitly that Fourier series are applicable to periodic signals. If we want to analyze a signal that is not periodic using Fourier methods, we cannot use the Fourier series. We must use the Fourier transform, which we'll get into later. Reading assignment, sections 3.2 and 3.3 of the third edition of Kamen and Heck. This is our course outline. We are up here in the Fourier signal models for continuous time signals, and we are still focusing on the Fourier series tool for periodic signals. And our goal, as we saw last time, was that by breaking a signal down into a sum of sinusoids, it provides us with a way of figuring out how each one of those sinusoids goes through a linear time invariant system. And since the system is linear, if we can figure out how each one goes through, each sinusoid in a summation at the front end, at the input side, if we can figure out how each term goes through, then all we have to do is add up those individual responses, and it'll tell us what the output looks like. So this seems to be an alternative to convolution, and in fact it is. And in one sense it provides an easier method than convolution, but even more important than that, it provides some really important insights into how to think about and design continuous time systems. And then later on we'll see similar kinds of ideas for discrete time signals and discrete time systems. Okay, so in the last set of notes, this is where we were. We had two different alternative but equivalent forms that we were looking at. So this one we called the complex exponential form, and we had the trigonometric form, and we said that those two things are equivalent to each other. And we talked about how last time we limited ourselves to n being a finite integer. So we were just looking at a finite number of terms that we were adding together. So here we're adding together real sinusoids, and here we're adding together what I call complex sinusoids, or complex exponentials, or rotating phasors. All those things mean the same things. And remember that the way we got to this term, or this form, was to take each of these cosines, split it into two parts, a positive frequency term and a negative frequency term, and then those two parts went into this sum. So the negative frequency terms were the negative integer terms in this sum, positive frequency terms were the positive integer terms in this sum. Okay, so we saw that we could build periodic signals with these forms with the finite integer n, and the question is, can we get any periodic signal this way? And without going into the details, the answer is that there are a lot of periodic signals that we cannot build with finite sums, that in fact we would need infinite number of terms to build things. So for example, a simple square wave, ideal square wave, cannot be built with just a finite number of terms. So without proving this, we'll just accept it that we need to go to an infinite number of terms. So if we take the two forms that we've already explored here and just let n go to infinity, so now we're summing from k equal to minus infinity up to k equal to infinity, where k are integers. So we're just summing over all the positive and negative integers. This is a Fourier series in complex exponential form. If in this form we let n go to infinity, we now have our sum that goes up to infinity. So here we're summing over just the positive integers. We're handling the k equal to 0 case out here separately. This is what we call the Fourier series in trigonometric form. So this form is discussed in section 3.2. The complex exponential form is discussed in section 3.3. These are just different forms of the same tool. So they are the same thing. And there is a third form that we'll see in just a little bit. We won't go into the details too much on that third form, but the three forms are completely equivalent, and a lot of it may just be personal preference as to which ones you actually use. But sometimes it's driven by the particular problem and what you're trying to do. So now the question is, now that we've considered an infinite number of terms, does that or this now let us get any periodic signal? And the answer is no. But Fourier, when he first thought these ideas up, thought that he could get any periodic signal. Fourier actually had a lot of difficulty convincing people that this was true. He was saying that he could add these together and create a square wave, for example. And a lot of leading mathematicians at the time felt that he could not create a discontinuous function like a square wave that discontinuously jumps, say, from -1 to +1 and then +1 back to -1 discontinuously. They thought that you could not build a discontinuous function by adding together a bunch of continuous functions, which were sine waves. But in fact you could. So Fourier was right in that sense. But later on there was another mathematician, Dirichlet, who showed that there are some functions that cannot be written in terms of a Fourier series. Some, I should say, insert here, some periodic functions that cannot be written in terms of a Fourier series. But the bottom line is we'll never see such signals in practice. So what we can say is that any practical periodic signal, we can write it as a Fourier series with an infinite number of terms. So, needing to go to an infinite number of terms may seem a little on the impractical side, but we'll see that we can handle, in many applications, we can handle analytically the infinite number of terms without any trouble. And in fact, numerically, now with computers, we can numerically compute with hundreds of thousands of terms if we so desire. And be able to get our answers just fine from that perspective. So this really doesn't give us any limitation as to the practical perspective of this. But furthermore, even if we couldn't practically deal with an infinite number of terms, the real beauty of this viewpoint of Fourier series and then later on Fourier transforms is not so much that we can compute with it, but more that it gives us a view of how to think about systems and signals that provides a great ability to think about designing systems. Okay, so what? We can expand any signal in terms of Fourier series, any periodic signal, practical periodic signal in terms of Fourier series. What's the great idea there? Well, we've already alluded to this. We can now take virtually any periodic signal and we can break it down into a sum of simple things. Those simple things are sinusoids. And those sinusoids have a very easy way of going through the system. We've already figured that out. So instead of taking some complicated periodic signal and analyzing it through convolution, we're now going to take x of t, break it down into its Fourier series components, and then just ask how each component goes through the system, find each of those responses, and add them up at the output. So that's what we'll be doing in essence. We'll be doing that in our heads. That's how we'll think about it. We can do it computationally, at least for some large number of terms in our Fourier series. So, we can think of this as being some sort of convolution evading analysis. We're trying to avoid doing convolution. So we're given a time domain signal model x of t. We can convert it into instead of having a time domain model, we can convert it into a frequency domain model. And by the frequency domain model, what that means is specifying the Fourier series coefficients, c sub k, or equivalently, the c sub k's are in the complex exponential form. We could specify the a sub k's and the theta sub k's, two sets for the trigonometric form. So what we're doing here is imagining taking our time domain model, which is the function of time, and converting it into a frequency domain signal model, which is just a collection of coefficients. So how do we do that conversion before we can apply this technique of analyzing systems using Fourier series by just asking how each sinusoidal term goes through? We need to be able to figure out, for a given x of t that we want to analyze the response of a system to that input, we need to be able to find its Fourier series coefficients. So how do we find them? And we're going to focus here on the exponential form. And then in just a little while I'll show you how to convert those exponential form coefficients into the trig form coefficients. And so the answer is just use this formula. And we can prove this, but we're not going to spend time to do that. I think the book goes through a proof of that, although I'm not sure off the top of my head. But the proof is not the important thing. The ability to do it, and even more important than that, the ability to understand why we do it, that's the important thing. So here's the formula. We take x of t, we multiply it by an e to the minus j k omega 0 t. We integrate over t from some time t0 up to some time t0 plus capital T. And I'm just pointing out that the book uses an explicit value for t sub 0, and that explicit value is 0. So I'm showing a little more general form here, which says that we can integrate over any complete period of the signal. So what is capital T? Well, remember, x of t must be a periodic signal here. So capital T is the fundamental period of x of t, and the units are seconds. From the fundamental period, we have to figure out what omega 0 is. So you get capital T by just looking at the function and identifying its fundamental period. You get the fundamental frequency omega 0 by taking 2 pi and dividing it by the fundamental period, capital T. And that will be in radians per second. So we now have the fundamental frequency of the periodic signal, x of t. T0 can be any time point, and you get to pick it. And you pick it to make your job easier. What's your job? Evaluating this integral. So we'll see in some examples that by proper choice of t0, we can sometimes make that integral easier. And what's the k that we put in up here? Well, it's the index of our Fourier series coefficients. So for the complex form, k must go over all the integers, positive and negative and 0. And so what do we have to do? An doubly infinite number of these things? Do we have to sit there and do these forever for the rest of time? No, we'll learn a method that will allow us to evaluate c sub k as a function of k. So we'll be doing this integral on the right hand side for an arbitrary value of k, and it will boil down, this whole thing will just boil down to something that depends on k. So once we have that function, then we'll be able to plug in the specific values of k that we're interested in and plot over some range of k what those c sub k's look like. So just to comment here, when we let k equal to 0, notice that we get e to the 0. E to the 0 would then be equal to just 1. And so this whole thing then goes away. And we're left with just the integral of x of t. So this is the result for c sub 0. It's just the average value, essentially, the numerical average value of x of t. If you were given a sequence of n numbers and you were asked to average them together, you would add them up and divide by how many there are. This is a similar idea. We're given x of t over a time interval of length capital T, so we add up the values, that's the integral part, and we divide by how long we have integrated. So this is a time average over one period. And in fact, we've already seen that C0 is the DC offset. So C0 is chosen to move the so that we end up getting a result that is kind of moved up to the or down to the right DC level that the original signal has. So what this tells us is that to find the DC level of a periodic signal, all we have to do is average over one period of that periodic signal. Okay, so summarizing the rules, we've pretty much seen all the heavy-duty rules that we need for the exponential form. So to convert back and forth between the time domain model and this one specific frequency domain model, which is the exponential form of the Fourier series, we use these two equations. So the analysis part of it is you give me x of t, I perform this integral, and what I get is c sub k. So I've given the signal, I'm analyzing it to find c sub k. This is like eating a food and figuring out the recipe. You go into a restaurant, you eat something, you go, okay, I think I could figure out how to make that. On the other side here we have the synthesis equation. It says you give me the Fourier series coefficients, all infinite of them, and I can sum this series up, at least in theory, and approximately in practice. I could go from minus 100,000 up to plus 100,000 if I wish. And so I'm using the Fourier series coefficients to build or synthesize the signal. I've been given the frequency domain model and I'm creating the time domain model. Over here I've been given the time domain model and I'm creating the frequency domain model. So remember, the time domain model is the periodic signal itself. The frequency domain model is nothing more than just the Fourier series coefficients. So we have similar equations to these for the other forms of the Fourier series. We've seen the other form of the synthesis equation for the trigonometric form. We have not yet seen the other analysis forms, but they exist. And we're not going to worry about them too much, because once we have the c sub k's, we can get all the other analysis results directly from the c sub k's. So you really only need to learn how to do this for the analysis. And then once you have those, you can convert it into all the other equivalent forms. So here's the relationships between them. And again, I'm not stating the forms for directly computing the coefficients. So over here we have the exponential form that we just saw. We know how to find the c sub k. So let's start there. Down here we have the trigonometric form that we've seen before, and that's specified in terms of amplitude and phase. So from the ck, remember the c sub k's over here are complex valued. We need to get real valued amplitudes and also real valued phases. And so how do we do that? Well, you take c sub 0 and set it equal to a sub 0. You take the c sub k, but you only need to look for the positive integers. Remember, c sub k is defined for all the integers. We only need to look at the ones for the positive integers. You take its magnitude. Remember, c sub k's are complex, so you know how to take the magnitude of a complex number, and then you multiply it by 2, and you get the a sub k. That multiplication by 2 right there, that is due to we're essentially undoing the division by 2 that came in Euler's formula that gave rise to the c sub k's. And then the other thing that we do is we take the c sub k's for the positive integer k's and just take the angle. Remember, c sub k's are complex. You know how to find the angle of a complex number, so you find the theta sub k that way. So now we've gone from the exponential form down to the trigonometric form. Let's say that we have the trigonometric form somehow. Maybe we've somewhere else learned how to evaluate the a's and the thetas directly, or maybe someone has given us that form and we'd like to find the exponential form from that. Well, we now go backwards. Again, c sub 0 and a sub 0 are the same number. Now we just look over all the positive k integers, because that's all that defines the a sub k's and the theta sub k's. And what we need to do is, for each value of positive integer k, just form the c sub Ck as according to this equation. Let me clear this up a little bit here. And then also, for each positive K, we form a negative K subscript on the C's this way. Notice that these form complex conjugate pairs. So as soon as you form all the CKs for the positive Ks, you know all of the C sub Ks for the negative Ks. So you've got C2, for example. C minus 2 is just the complex conjugate of C2. Okay, so that's very easy to do. Let me clear this up here again. Let's go from the complex exponential form to a new form, another form of trig form, which is sine cosine. So here we have A0 out in front for our DC offset. We're still summing over just the positive integers, just like in this trig form. But here we have two terms. Each term of the sum consists of two individual terms. One is a cosine term, one is a sine term. And what we can do is specify how to calculate these Fourier series coefficients. We've got the A sub k's and we've got the B sub k's. So we can get there from our exponential form by, again, A sub 0 is equal to C sub 0. The A sub k's are just 2 times the real part of C sub k for only the positive k's. B sub k is just minus 2 times the imaginary part of C sub k's. And we can also go from this trig form to this trig form using this result. Actually, this says A0 is equal to C0, but we know that capital A0 is C0. So this term actually here should be capital A0. Kind of a rough A sub 0 there. So it's the same as this. And so then we can find it using this equation or this equation, these two equations to get the A sub k's and the B sub k's. And we can go backwards. Notice that these look an awful lot like conversion between rectangular and polar form. And in fact, they are very much like converting between rectangular and polar form. Okay, so again, we will focus mostly on the exponential form. These other two are more from the perspective of real-world visualizations, or if you wanted to actually physically build something in the lab or in a situation like that, you could use either of the trig forms. Let's clear this up just a little bit here. If we notice that the difference between this trig form and this trig form, up here we have both a cosine and a sine, but each of those have 0 phase. So there is a result that says if you add a cosine and a sine together with different weights out in front, that you can express it as a general cosine with some weight out in front and some phase shift. So that's really what's being done to convert between those. Those are just some trig identity ideas. If you look at the trig identity table that I've posted on Blackboard, you'll see an identity that is responsible for that conversion. Okay, so we have now the ability to find the Fourier series coefficients, at least for the complex exponential form. And once we have those, we can convert them into the other forms if we wish. Right now I want to try to convey to you, an example, an illustration of how an engineer might use these Fourier series ideas in a design problem or in an analysis problem. So one simple electronics problem that you may have encountered in your electronics class, if you've already taken one of those or are currently taking one of those, you might want to create a DC power supply. And this is just one simple way of creating a very simple DC power supply. So DC power supply is what we want to create. We're going to use diodes and a simple RC filter circuit to create this, as well as a transformer. So we have 60 hertz sine wave coming out of the wall. So this is my attempt to draw the picture of a plug that goes into a wall socket. In the US anyway, we have 60 hertz. Elsewhere, there are places that have 50 hertz. In the US, we have 110 volt RMS sinusoid. So that's the RMS value. You should already know how to convert that RMS value into the peak value. So from 60 hertz, that's 60 cycles per second. So in if we think about one cycle, let's see, one we're going to take 1 divided by 60 cycles per second. We're just going to take the reciprocal of that. So this 1 is really kind of, one cycle. Then we end up getting 60 cycles per second. The cycles cancel, and we get 16.67 milliseconds. So that is our period. So our fundamental period, don't know quite why I called it T sub 1, but we'll see as we progress through this if I use a different subscript. I think I did, actually, yeah. We have a different subscript later on. So we have a sinusoid whose period is 16.67 milliseconds. So that's what's here at the other side of this transformer. So this component right here that's the schematic diagram for a transformer. So it takes this 110 volt RMS sinusoid and it'll convert it down to some lower amplitude, whatever is appropriate for the type of DC level that we're trying to make. So this height here, I haven't specified what it is, and for this design or analysis we don't really care so much what that height is. So what that's telling us is that one cycle, so here's one complete cycle of the sine wave, takes 16.67 milliseconds. So this structure here is what's known as a full wave rectifier, and I'm not going to go through the details of how it operates. You should have seen that in your electronics class. If you haven't already seen that in an electronics class, don't worry about it. Just trust me that the signal that goes in across these input terminals here, if you put a sine wave in, what comes out across these output terminals here, we'll call x of t, just looks like this. So here's the first half cycle of the sinusoid. Nothing happens to it. The second cycle of the sinusoid, which goes negative, this circuit turns it upside down and makes it positive. So basically what it does is it takes all of these, let me clear things up here a little bit. It takes all of these humps on the bottom and just flips them up so that we get something that looks like this. So now we have a periodic signal, but it has half the period of the original. Remember we had that this had a period that went through both a positive going hump and a negative going hump. This rectifier made out of the diodes takes the negative hump and flips it up, which then looks exactly like a positive hump. So we now have half the period. So our period of this periodic signal is now 8.33 milliseconds. So this is the signal that goes into this RC filter, and we ultimately want to figure out what comes out. And we're just going to assume that this has 0 initial conditions. If it didn't, we could figure out the initial conditions. But remember, we've already seen that when systems have initial conditions, good systems, stable systems is what we call them, the response to the initial conditions die away. So if we're only interested in how this thing's going to behave, in the long run, after that response to the initial conditions dies away, which is usually pretty quickly, we can often just assume 0 initial conditions and analyze it for that case. So we want to find out if the signal goes into the RC circuit, this full wave rectified sine wave goes into the RC circuit, what comes out? And on the basis of doing that analysis, we can then choose specific RC value so that we get what we want. So for now, we're just going to do the analysis of the input side, and then later in Chapter 5, we could use it to figure out what comes out and how this thing behaves. So let's just do the Fourier series analysis on the input side for now. So the equation for the Fourier series coefficients, we've already seen, is this, where the omega sub 0 is specified this way. So for our problem, we're going to choose t sub 0 to be equal to 0, because then we can start integrating right here. We wouldn't want to start integrating somewhere here and go one full period, right? That would make things difficult, because then we would have one functional form here, and then we have a slightly different functional form. If we start at 0 and we integrate for one period, we're just going over one sinusoidal hump. So we're going to pick t sub 0 here and go one period forward, and it's over that integral, it's just one functional form. So if we chose t sub 0 somewhere in the middle there, that would make things considerably harder. We'd have to split our integral into two different integrals. We would integrate from here, where we start, up to there using one functional form for the integrand, and then we'd have to switch to a different functional form from there to there, and that wouldn't be good. Okay, so what is the equation over this period of this interval of integration, 0 to capital T? Well, we're just going from here to here, and that's just the sine wave. Remember, the sine wave continued down here like this, but we're just looking at the first half. So it's just a sine of pi t, pi over t times little t, and that's valid over that range. So we just get that by looking at the plot and understanding how we got this function from the original sine wave. So now we're just going to take this result for the sine wave, for x of t over that interval, and we're just going to plug it into here. So we plug it in here. We've plugged in our specific result for omega 0, so we have that now. And so now all we have to do is evaluate this integral. And we look at that and we say, yuck, that looks a little yucky, maybe a little bit hard to do. And we're going to evaluate it as a function of k. So we're going to leave k arbitrary. Now in some situations, it makes sense to try to attack this maybe sometimes for two subclasses, or maybe even more than that. But we might want to consider what happens when k is even, what happens when k is odd, things like that. So keep that in mind. But in this case, we don't really have to do that. So to evaluate this integral, our job first is to make it simple, to make it easy to deal with. And so the first thing we're going to do is just try to do a change of variables. Why do we decide to do that? Well, we look at the thing that's the functional form of, or the argument of sine, and we see, well, there's an awful lot of stuff in there, and it differs a lot from the stuff that's out here. Let's do a change of variables to just try to simplify this down as much as we can before we try to look this up on a integration table. Now, you may be lucky and be able to look this up directly on an integral table, but let's do the change of variables, if for no other reason than to remind you of how it's done. So change of variables is just a trick that we use to try to simplify the form of an integral before we actually try to do it. And there's three steps. Identify the new variable and substitute it into the integrand. Then we have to determine the impact of that substitution on the differential, so that's the dt. And then we have to determine the impact of that substitution on the limits of integration. So that's these things. So let's take a look at these. Step 1. We're going to, up here, look and say, aha, let's grab all the stuff that is inside the sines argument, and we're going to just replace it by a single variable. So we're going to say pi over capital T times little t. We're going to set that whole thing equal to tau. So it's just saying that tau is a variable that changes as t changes, And if I make a 1 unit change in t, I'm going to get a pi over capital T change in tau. That's all that says. So we're just changing from one ruler to a different ruler. It's like changing from a ruler in terms of inches to one in terms of centimeters or something like that. So when we do that, we make that substitution everywhere in the integrand. So notice that we have it here as the argument of sine. So we replace sine of all that stuff by sine of tau. And we also notice that we have it here. So all of that stuff is the same stuff except without the 2. So we would have pi over capital T times little t. That's tau now. So we have 2 tau, and we keep the minus jk. So let me clear some of this stuff up. Now we have, this is our new integrand. And look, it's a heck of a lot simpler than what we started with. Okay, step number 2. Determine the impact of this change on the differential. Well, we start from here, and one thing that you can think of is treating tau as a function of t. So if we took d tau dt, this is a simple linear function, so d tau dt is just equal to pi over capital T. Then we swing the dt over to the other side. So remember, d tau dt is equal to pi over capital T. Swing the dt over, and we get that d tau is equal to pi over capital T dt. Or solving this for dt now, which involves taking this thing and bringing it over to the other side by flipping it, we now have that dt, which is what we had as our differential, is just capital T over pi times d tau. So now we can substitute that in for dt. So we'd get an extra constant that we'd have to pull out in front. Step 3 is determine the impact on the limits of integration. So again, remember, it comes from here. This was our substitution. So when t is equal to 0, we plug 0 in there, and we get that tau is equal to 0. So I've plugged 0 in for t, and I get that tau is equal to 0. That makes sense. Again, I'm just changing rulers, so something that is 0 on one ruler is going to be 0 on another ruler. And now I want to take this limit, capital T, and find out what it goes to. So when the variable that I used to integrate over, t, little t, takes on the value of capital T, what does my new variable of integration do? Well, here's the equation. I plug in capital T here. I get that it's equal to pi. So my new limits of integration are 0 and pi. And so using all of this, let me clear this up here. Using all of this material here, we have our new integrand. So here's our new integrand. We have, this top line, by the way, is just the original integral. We have our new differential. So we've plugged in for dt. We've plugged in all of this stuff here. So we have that. This constant can be pulled out in front. We'll do that in just a minute. And we have our new limits of integration. We integrate from 0 up to pi. And there we have it. Let me clear up things. And so now we've just got a little bit of manipulation to do here. We can pull this t out in front here, and notice that it cancels with that, so that cancels. We pull the a and the pi out in front, and we get this constant a over pi times this integral, the integral from 0 to pi sine of tau e to the minus jk 2 tau d tau. There's our new integral that we have to worry about. So I've just rewritten it up here. Here it is. That's the thing that we have to do. You can now go to your favorite table of integrals, and it's likely that you'll find that there. And in fact, there's one available on the course website, and I'm pretty sure this form is on there. Maybe not exactly with these symbols, but it's on there. So this is a general entry from an integral table. Says you have some sine with some frequency times some exponential with some decay rate. So a is the decay rate, B is the frequency. So for our case, that's exactly what we've got. We've got a frequency of 1, and we've got a decay rate of, well, the whole alpha is going to be minus jk2, right? So we can now use this specific thing. So A is going to be equal to minus jk2, or in this case j2k. B is equal to 1. We plug those in. So this is the value of the integral, the indefinite integral. So we put that inside these brackets. We've just evaluated this for these specific values, and now we have to do the definite integration part where we evaluate this at those two limits of integration. So before we go off and do any of this brute force, and you always want to try to finesse the problem, look for shortcuts. Don't just blindly plug things in. Don't just blindly evaluate things with your calculator. You'll end up taking a lot more time than you need to, and you'll miss important insights. So the first thing we see here is that, well, we're going to have to be evaluating sine at pi and 0. Think a minute. Tick, 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 tick. Yes, okay. Both of those are going to be equal to 0. Sine of 0 is 0. Sine of pi is 0. So that whole term, this whole thing right here, we can ignore because the two places we're going to evaluate it are equal to 0. So we can just imagine that this whole term just goes away. We don't have to fuss with it anymore. So now all we have is this exponential times a minus cosine of tau over 1 minus 4k squared. That's what we have to evaluate. So we can now do this. I've pulled the minus sign out in front right here. And this is the thing that we now have to evaluate. See how much easier that is? I've also pulled the 1 minus 4k squared out in front because it has nothing to do with the evaluation. So why carry that through all the evaluation? Pull it out front. I'm evaluating at values of tau. So there's no tau in there. Pull it out. Okay, so now when we do that, we're evaluating at pi and 0. So here is that term evaluated at pi and evaluated at 0. And these are very simple evaluations. E to the minus j 2 pi k. Well, I've got an integer times 2 pi sitting up in a complex exponential. It's telling me that it's integer multiples of 2 pi. So 0 times 2 pi, 1 times 2 pi, 3 times 2 pi. They all put me at the same place on the complex plane. Where are they putting me? Here's the real part. Here's the imaginary part. And where is that putting me? It's putting me right here at this point. That's equal to 1. So I know that that result is equal to 1. Again, that's one of our special unit circle points. Cosine of pi, well, another special thing that we should know. Cosine of pi is equal to minus 1. So this whole thing is just minus 1. And then e to the j blah with a 0 in there, that's just 1. Cosine of 0 is 1. So we have a minus 1 minus a plus 1. That all adds up to minus 2. A minus from the minus 2 right there cancels with that minus, and we're left with this result. So there is the evaluation of the Fourier series coefficients for the complex exponential form for the full wave rectified sine wave of amplitude A. So A was the height of the sine wave that went into this thing. So just some comments here. We evaluated this in terms of arbitrary amplitude, arbitrary period, and therefore arbitrary fundamental frequency. And as engineers, you should get in the habit of doing that. Year after year when I teach this course, students are always complaining that they want to see and they want to do examples and problems that have specific numbers in them because they have a difficult time dealing with problems where the parameters are left arbitrary. You really and I cannot stress this enough, you really need to learn how to do these problems with arbitrary constants, because that's what design is all about. You have maybe a specific structure in mind and you need to solve or determine specific parameter values. If you can't manipulate things and solve for results in terms of arbitrary parameters, you'll never know what your design space looks like. So for this particular example, we may not yet know what the frequency of this is, or we may be trying to design simultaneously for a 60 hertz system and a 50 hertz system. If we're an international company trying to sell our wares in two places, we need to come up with two different designs. So we notice that this result here does not depend on t. T was the fundamental period. So there's no dependence of the Fourier series coefficients on the value of t. We note that ck is proportional to a. We also see that the coefficients have this inverse quadratic relationship to k. So these two insights, general arbitrary insights, tell us that if you change the input sine wave's frequency, the c sub k result doesn't change. Where those c sub k's sit in frequency change, but the values do not change. And the other thing is that if you change a, you change the c sub k in a proportional way. So if you double a, you'll double c sub k. If you triple a, you'll triple c sub k. If you evaluated this all for a specific numerical value of a, you would not see this insight that would allow you to then essentially solve a whole class of problems. So imagine this: your boss, your manager, gives you a problem and you say, well, I'm going to solve this for the specific values that he just told me, he or she just told me, and you solve it. And then your boss comes back and says, oh, never mind, instead of 5 volts we need it for 10 volts. You'll have to redo your work. Well, you'll impress your boss if you can immediately say, oh, you've just doubled it to 10? Well, just double the c sub k's. That's what good engineers do. That's what you need to learn how to do. Well, so now we have the c sub k's, and remember, in general, these are the coefficients for the complex exponential version of the Fourier series. So in general, the c sub k's are complex valued. So we plot these on our spectrum plots using magnitude and phase ideas, treating these things as polar form complex numbers. So we need to find magnitude and phase. So what does this mean when we have c sub k's being real for this case? Look at the form for c sub k. So right here we see that our c sub k for this problem is purely real. Does that mean we can't find magnitude and phase? No, of course we can. Remember that the real line is embedded in the complex plane. It makes up one of the two axes of the complex plane. So every real number just happens to be also a complex number that has a very specific structure, and we can exploit that. So let's look at this. So for c sub 0, we're going to look at this for two cases, for k equal to 0 and k not equal to 0. So for k equal to 0, this term goes away, and we're left with just 2a over pi as a number. A was strictly positive. We knew that because that was the amplitude of the sine wave. And so we don't need to take any magnitude to get the magnitude. So the magnitude of C0 is just 2a over pi. It's a positive number. And since the thing that we get, so C sub 0 without the magnitude is also just 2a over pi. Positive real number, I claim that its angle is 0. Why is that? Well, here it's a positive real number. Where is it? What's its angle? It's 0. So any number that is real and greater than 0, its angle is 0. Now let's look at the case when k is not equal to 0. Now remember, k, let me clear this up here, k ends up showing up in a square form, so c sub 2 and c sub minus 2 will be equal to each other. So we only have to worry about analyzing one side of these. So let's do that. When k is not equal to 0, let's say that even just for k equal to 1, we get a 1 minus 4. So this quantity here will be negative. And in fact, as k gets even bigger, this quantity gets even more negative. So let's, when we take the magnitude, we've got to undo that negative part, right? That's just the idea of taking the magnitude of a real but negative number. Treated as a complex number, magnitude and absolute value mean the same thing. Okay? So, turning this into, or taking the absolute value of it is the same as negating it, which just reverses the order of those. So the magnitude of c sub k for k not equal to 0 is just given by this quantity here. Okay, and now the question is, what is its angle? Well, like I said, c sub k for k not equal to 0 is a negative number. We've established that already. So that means it lives over here on the real line, and its angle is either going to be plus pi or minus pi. Doesn't matter. Either one is correct. It's your choice. So the spectrum that we had before the rectifier, so this is the sine wave coming out of the transformer, was a single input. Or I'm sorry, a single sinusoid. Of course it was a single input. So a single sinusoid, to express its spectrum, there's just one sine wave term, the thing, right? And we're showing it at, it was at a frequency of omega 0 over 2. Remember, omega 0 is relative to the period of the rectified sine wave. Remember, the period of the rectified sine wave was half the period of the original sine wave. That means the frequency of the original sine wave is half the frequency of the rectified, the fundamental frequency of the rectified signal. So the omega sub 0 comes from the reference of the rectified signal, came from finding its periodic, its fundamental period, and then finding the fundamental frequency. So that's why we divide by 2. So it was a sine wave. We just assumed it was zero phase. So we have something that looks like that. The frequency that comes out, or the stuff that comes out, is rectified, and we calculated these values and we calculated these phases. So these are a frequency domain characterization of the signal that comes out. Notice that something is interesting here. This is unlike the linear time invariant system. A linear time invariant system, we said you put a sine wave in, it comes out as a single sine wave, same frequency. What are we seeing here? Going into the rectifier, a single sine wave goes in, what comes out? Lots of sine waves. So a nonlinear system can create new frequencies. A linear time invariant system cannot create frequencies. And I say that soon you should be able to explain why that is. We've already really seen that. We've analyzed the impulse response, or we've analyzed using convolution and the impulse response when a sine wave goes in. Sine wave goes in, sine wave comes out, as long as that sine wave is imagined to be infinite duration. Okay, so there are some important practical and conceptual ideas that we just mentioned here. So make sure you've got a grasp on those. The reason that we put a sine wave into the rectifier and we get many sine waves out is because it's nonlinear. A linear system, you put one sine wave in, you cannot get more than one sine wave out. Okay. So now we can find the trigonometric form, if we wish, of this Fourier series. So once we have the c sub k's, we can use this general result that we've already seen. And so the rectified sine wave has this trig form. And so we can then plot our one-sided spectrum of this. So it looks like this. There's our magnitude spectrum and our phase spectrum. So this is a expression for the input to an RC circuit that comes after the rectifier. We can imagine that the input, well, we know physically it's just this full wave rectified sine wave, so it's just these repeated positive humps of a sine wave, one right after another. That's one way of thinking about it, and if you think about it that way, you're going to have to do convolution. Convolution might be difficult to compute in that setting. Now we can see that instead of thinking about it as that series of positive sine humps, instead we can think about it as an infinite sum of sine waves. And we can use superposition concepts so that we can figure out how each one of these terms goes through the RC filter. And then once we've figured out how each one of those terms goes through, all we have to do is add up each of those resulting responses and we get the output. And we'll do that later on. Okay, there's a theorem for Fourier series that's presented in the book called Parseval's theorem. I'm going to first present some preliminary ideas that lead up to the idea of Parseval's theorem. And these preliminary ideas are not in the textbook. So, from your circuits class and your physics class, if we have x of t and we view it as a voltage, and we apply that voltage across some resistance R, we can state an equation for the instantaneous power. By instantaneous, I just mean it's power as a function of time. So as the voltage changes, the amount of power that's being applied to this resistor, or equivalently dissipated by this resistor, is just the voltage squared divided by R. Okay, so we've got that idea. Now in circuits, we haven't been talking about any R's per se. I mean, we've said that we have RLC circuits and so forth, but we often just want to specify kind of the size of a signal. How big is it in some sense? How strong is it? So some measure of the strength. And power in physical systems describes also some sort of measure of strength or bigness of a signal. So we'd like to just kind of use this idea but not have to worry about tying it to some physical resistance in which the voltage exists, or across which the voltage exists. So we can imagine that we're just normalizing away any physical resistance. So by normalizing, we'll put this subscript n here, and we're just going to ignore the effect of the R value. Or in other words, we're going to take this whole quantity here and essentially we can just normalize it to unit resistance. So if we once we've normalized it to unit resistance, if we know that we do have a specific R, we can always unnormalize it by dividing the normalized power by R. But we're typically not going to do that. So in signals and systems, we're not going to worry about any of this. We're going to drop the subscript n, and we'll just say that P of t is equal to x squared of t, with the understanding that we're imagining that this is a unit resistor that this power is related to or occurring within. So if you recall the relationship between power and energy, power is a rate of energy, so it's the energy per unit time. And to drive that home unit-wise, power can be measured in watts. Energy is measured in joules, and 1 watt is defined to be 1 joule per second. So if you are supplying energy at the rate of 1 joule per second, you are providing 1 watt of power. So it's important to keep that in mind. We tend to think of power as this quantity thing, a bunch of stuff, but in reality power is a rate at which you're providing energy. So what that means mathematically, we can write that power is the time derivative of energy. So if energy is changing as a function of time, so we write it as a function of time, we can find that rate of change at each instant of time, and that is the instantaneous power. So we now know that dE of t dt is equal to x squared of t. And if we swing the dt over onto the other side, we now have a differential increment of energy, dE of t. So we know that that differential changes by different amounts at different instants of time. And so that's just equal to x squared of t dt. Great. We want to know the total energy in one period of some periodic signal. So now we're switching to our focus being periodic signals. The stuff that came above was just all general. So over one period, so you start at some arbitrary little t0 and you go up to one period past that, you just integrate the differentials of energy. Those are the small differential increments of energy. And by increment, it could be increment or decrement, depending on whether it's positive or negative. So this quantity here, we're just writing out to show what we're really doing. So that is just a statement that it's the energy in one period of this periodic signal. But using this result here, the x squared of t dt being equal to dE of t, this integral that we say is the energy in one period is just written that way. So let me clean things up here. So what we have now established is that we can find the energy in one period through this equation. So that's an important equation right there. Probably should have had that set off by itself. Energy in one period is given by integrating this square voltage, or current for that matter, over one period. If we want to know the total energy of a periodic signal, we integrate it from minus infinity to infinity. Now, picture in your mind any periodic signal, and we're going to square it, so now there is no negative area that can be contributed as we go through this integral. So we're just constantly accumulating positive area, and we're getting the same amount of positive area from each period, and we're going through an infinite number of periods. So we've just established through a simple argument that the total energy of a periodic signal is infinite. So we usually focus just on the energy in one period. So we state the energy in one period. It kind of gives us an idea of how strong is this signal. Okay, again, remember that power is equal to energy per unit time. So if we want to know what our average power over one period is, we would take the total energy in one period and divide it by the amount of time. In the same way that if we knew that we were going, we were driving in a car and we wanted to know what our average time was, we would take the total distance. We wanted to know what our average speed was. Remember, speed is a rate, power is a rate, so speed and power, I'm drawing an analogy. We would take the total distance, so energy and distance are playing the analogies here. We would take the total distance and divide it by the time that we spent driving that distance. That would give us our average speed. Same kind of thing. If we want our average power over one period, we would take the energy in one period, which we just figured out how to compute, and we would just divide it by t. So the integral here gives us the energy in one period, which we just saw, and now we're going to divide it by capital T, that's the period, and that will give us the average power over one period. So we often just call this the average power. And in fact, we often just drop the average and we just call it the power. So the average power over one period of a periodic signal can be found by integrating the square of that signal over one period duration and then dividing by the period. Okay, so as I've already stated here, For periodic signals, we use the average power as a measure of the size or the strength of the signal. And we've established here that the average power of practical periodic signals is finite and non-zero, but that the total energy of a periodic signal is infinite. Okay, so now that we've set the stage that way, we can now talk about this thing called Parseval's theorem. And Parseval was, again, another mathematician, 100 or more years ago. I don't really recall exactly when Parseval was alive, but a long time ago. So we've just seen how to compute the average power of a periodic signal given its time domain model. So you tell me its time domain model, so you tell me x of t. I have to square that model, integrate it over one period, and divide by t. Then I get the average power of a periodic signal. Parseval asked the question, can we compute the average power from our frequency domain model? And so, in this context, our frequency domain model is the Fourier series coefficients. And we're doing this particularly in terms of the complex exponential form, where we need to know these for all positive and negative integers k. So Parseval's theorem says yes, and it doesn't just say that we can, it tells us exactly how to do it. So Parseval's theorem says this. This is the average power. We could compute it this way, but Parseval says we can also compute it this way. So we take the c sub k's. Remember, they are complex valued coefficients. So we take their magnitude, so we think about them in polar form, take their magnitude and square it, and add them all up over all the positive and negative integers. So this is another way to compute the average power. It allows us to look at a plot of the Fourier series coefficients and get an idea of how much power is being contributed by each of the different Fourier series coefficients. Just in the same way that we could look at a plot of the time domain function and say, well, these, in this section of time, maybe in the first half of the period, we don't get any energy contribution or any contribution to the average power. But in the second half of the period, we get a lot, that kind of thing. We could now say, well, at certain frequencies, we get very little contribution, but at other frequencies, we get a very large contribution. That's what Parseval's theorem lets us do. So another way of writing Parseval's theorem is just writing explicitly, leaving the p out of it, saying that this is equal to this. So we just have these two things. Notice the structure here. Remember that we can think about integrals as some sort of super sum. We have essentially a sum of squared values, a sum of squared values. So in each domain, the idea is summing squares. So that's what we're stating here. We can interpret Parseval's theorem as being a sum of squares in the time domain model or a sum of squares in the frequency domain model. So x squared of t, the thing that we're quote-unquote summing up, really integrating it up, that's the power at time t, and it includes effects at all frequencies at that time. So this is, if we see a small value for this at that instant of time, we're contributing very little to the average power. But if we see a large value of that at some other time, then that time point is contributing a large value to the average power. Likewise, this number here is telling us the amount of power at the frequency k omega 0. And so it includes the effects of all times. So when we see a small value of magnitude squared of c sub k, that's telling us that at that frequency, k omega 0, we have very little power being contributed at that frequency. But if we see a large number for c sub k magnitude squared, then at that frequency we interpret that as a large contribution to the overall average power. So what this allows us to do is to be able to see where in frequency the power is concentrated. And in practice, that's extremely important. if we're creating a signal and we need to say, for example, transmit that signal over the radio airwaves, the FCC controls how much power we can have in certain bands and how much power is allowed to slop over into other bands. So, for example, a radio transmitter would be under FCC regulations. The FCC would say you are allocated maybe a 200 megahertz bandwidth centered at, say, 200 kilohertz bandwidth centered at 99.1 megahertz. You need to be able to ensure that the signal that you're sending out has most of its power. And the FCC will tell you how it defines most, but you need to have the vast majority, maybe 99% of your power within your band, and the remaining 1% can actually fall outside of your band. So for periodic signals, this viewpoint allows us to see which amounts of power, how much power lies within our band and how much power lies outside.